right, now we will hear from Dr. Tzu Chieh Wei, my esteemed colleague, who will speak about what is quantum computing.
Thanks, Angela. So good morning, everyone. So I'd like to see the audience, the teachers. What are you teaching? Anyone teaching physics, chemistry, computer science, and others that I have not mentioned? Biology? Research? Engineering?
I'm teaching the first wave of the quantum computing.
You're teaching quantum computing. Great. So you see the title. So my colleague and I, we'd like to step back, because you have heard a lot about quantum computing, quantum information science and technology, engineering. We want to step back and tell you a little bit a gentle introduction to the subject so you have better ideas. So you see the title, Quantum and Computing. It's already interdisciplinary. Quantum comes from which field? Physics. Computing?
Physics.
Okay. It started with physics, but it's classified in computer science, right? If you trace back, maybe everything would be physics. Chemistry also traced back to physics. Biology, it's hard to explain by physics, but I'm not. Okay, but this is good discussions. So, but it's all about science, right? So quantum computing is really interdisciplinary, as we all pointed out earlier. And why is it important? So I'm going to try my best to give you an idea, and hopefully you have intuitive understanding of the two questions that I posed. Okay? If any question, you can raise hand during my talk. Just interrupt me. So I want to bring back computer, the classical computer, laptop, cell phone. It uses chips. You probably know this Moore's law, right? This is Gordon Moore who proposed that the number of transistors on chip would roughly double every 2 years, maybe more precisely 18 months. And here is a graph that I took from a paper already a long time ago. If you extrapolate the trend, you see that the size of a single transistor would hit the size less than a nanometer, and would be roughly a few numbers of atoms, right? It's quite small. At that scale, we're not sure the current technology would function the same way, right? So this might be the demise of Moore's law or classical computing power, because you cannot cram too many chips, and then we will we'll stay flat at our computing power, which could be a threat to our human technology. This means that the quantum regime is inevitable, because we learned about quantum physics at the level of atoms, right? And then people turned around quite early in the 80s. The question is, can you process information using quantum rules? And so fast forward 40 years after that, you already see a lot of quantum computers and leaders, simulators emerging, created by industry in mass scale. So for example, these IBM 127 qubit, Google's 105, etc. So it opens up a lot of possibilities. So we want to ask, what are quantum computers? What are they made of? Okay, you see this various prototype here, and what are they made of? The answer is depends. There might be future quantum computers that are not made of materials or items that are listed here. But currently, they build upon atoms, ions, even the precious diamond. You have defect there. It's actually a precious thing because it can host quantum bits, and superconducting materials. And how are they operated? You know, you learn from classical computer science, you use bit 0 and 1 as information carrier. So we talk about in decimal, like 10, 15, but computers speak like 0, 1, 0, 1. If I talk to you, I would say 0, 0, 0, 1, 1, 1, 0, 1, 0, 1, 0. But it's hard for us to process. So that's why there is a translation from what we need to put into computer and how they operate, right? But that's their language. So you see this logical gate. How you act on them is using these logical gate. They are made by semiconductors, chips, etc. So you see that you have 2, 1 comes in, you do the AND operation to become 1. Okay? Quantum computers, they use quantum bits, and they use quantum gate to operate. In fact, everyone has a quantum bit at the table, right? There's prototype quantum bit. So it can imagine as a sphere, an arrow pointing the sphere, representing a quantum bit. And you have a quantum gate that may be created by external magnetic field or pulse that change the state of the quantum bit. And then at the end, you need to know the outcome. You have to read out, right? So there's meter representing the readout. And in our summer camp, we teach students about 3 key quantum mechanical rules. For example, superpositions, unitary evolution, meaning gate, and measurement, meaning readout. And they can be entangled. This might be Schrödinger cat we saw earlier, and you'll hear from Dr. Snebler later. So you have a sense of, I hope you now have a sense of what quantum computers by extracting the analogy to classical one. In short, it just adds the word quantum. Okay. But these are the 3 principles that we teach in our summer camp. So I'm not going to go through the detail. We use the various representation, for example, polarizations, electron spins, and I even use quantum coin. Superposition basically means that you can be at different places at the same time. So it's, for example, the coin could be simultaneously up and down. Okay? Unitary gate is something that changes the state of, for example, polarization or the coin. You flip the coin, the gate, classical gate, you flip the coin, you turn on the switch, turn it off. Quantum, you can actually act on it simultaneously, right? So you can make this, for example, you think of horizontally polarized light, you can turn it into circularly polarized light. So these are represented by these symbols, and ultimately it can be represented by this sphere. It's more than just what I said here. And of course, readout. I always have to, we use our eye to read out, but for quantum computer, you have to use some gadget devices to read out. We use the representation in the polarizing film that the light would get projected in one direction. That's a readout. But this is probably too much. I don't want to make you that you have to remember all these. We sort of spend 2 days in our camp to get to this stage. Okay. But welcome to send your student to our camp. So the next question is, what can they do? So they utilize many qubits. So there is a lot of space. We call Hilbert space. It's a huge information storage space. And massive parallelism, because you could use superposition. It's like your brain can work on, maybe let me put this analogy. There's a kid who can actually play chess with hundreds of people. His brain is probably in the massive superposition and utilize the perhaps quantum parallelism, from superposition and entanglement to solve difficult problems like playing chess, etc. It's much more efficiently than any classical computer. So that would be an analogy of a quantum computer, that the kid who can play 100 chess games at the same time. And so what can they do? They can do some computational tasks much more efficiently almost exponentially faster. For example, factoring and solving large linear equation. However, it's still a research that we still do not know their full potential, and also limitation. We have to look at both sides. And it's still being investigated, and many more applications are still being found. And this could be found by the student here or your future students. So I would maybe give an example of factoring. So, but limitation is that the current quantum computer is still far from perfect. There are noise, errors that cripple their performance. So we call them noisy intermediate scale quantum devices. You may heard about NISQ if you go to a professional conference. You just say, oh, what about a current NISQ quantum computer? They will be amazed by your knowledge. So I want to particularly emphasize factoring. It can easily break some encryption called RSA. But I want to also point out this threat posed by quantum is actually solved by quantum. You can actually use quantum to perform quantum key distributions. You heard about a talk by our distinguished Professor Eden Figueroa on his internet that could enable this quantum key distribution. So I want to point out this RSA. Who have heard of RSA? I would think students would have probably heard. Not many, but this is a public key crypto system. This is the oldest widely used secure data transmission. So there are two keys. You have a secret key and public key. The public key is for someone want to send information securely to you. They use this public key to encode, and you have the secret key to unlock. And if you want to verify your identity, you can encode something for the public key user to open and see that verify that this is a message. Yeah, and they rely on two large prime numbers, but you only know the product, certain product of them. So the prime number are kept secret, but there are derived two keys from them. Okay, so therefore it's very important because it's used in internet where I'm downloading my slides, even though there's no sensitive information. Maybe I want to protect that. Okay, maybe it's from the company or from the secret agent, or you want to protect that information. Not from my slide, okay? And browsers, and banking, cell phone, secure communication, a lot of places, right? Even while you're browsing, you are looking at your cell phone, you're actually using RSA in the background. So this security relies on that factoring a number is very difficult, even though it's composed of two large prime numbers. So this is factoring problem. So who knows how to factorize this number? 15, 3 times 5. Easy, right? 20, okay, slightly larger number, 221, 13 times 17. Right, still easy. And you can solve by your computer. Oh, how about this one? This is a really large number. If I tell you it's actually composed of product of two prime number, it's still challenging to solve. This is called RSA 250, has 250 decimal digit, or 829 bits. So this is a hard problem. And we rely on that factoring this is hard. Therefore, there is a security in the encryption using the two keys. Okay, so students in our camp learn about the idea of encryption, decryption, and quantum key distribution, roughly on the 4th day of the camp. So I mentioned this RSA, right? It was actually factorized. This 250-digit number was factorized by these people in 2020. So the answer, let me announce to you, is this two large number, prime number. You you can actually easily verify by multiplying these two numbers and to get this. But from top to bottom is a hard problem because they use approximately 2,700 CPU core years, not hour, years, to solve that. Okay, and there are even larger number for you to solve. Some come with a cash prize, 270 digit cash prize of 75,000. So it's hard. But Peter Shor was a mathematician who proposed a factoring algorithm based on quantum mechanics. Although he did not have a quantum computer at that time, but in his head he could process that kind of thinking. He said, I can actually do it much better. How much better? Let me just, using my estimation, drawn from the performance, if you have an ideal quantum computer, but to be on the same ground, let's just assume classic computer can factorize 30 digit, 30 seconds, quantum also 30 seconds. And you see the dramatic difference starting as you increase number of digits, right? So let me just highlight RSA to 50. Let's assume it's factorized in year, like real time year. You may have a lot of computer adding to the CPU core hours. Let's assume that it can be factorized in a year by our classical computer. For quantum, it's less than year. So maybe a year is 10 to the 7, so this is not even a month more. Yeah. It's really fractionally of this, right? Right. Roughly 1,000 of this. So it's not maybe a day or something. If you look at the cash price, this is another RSA 2048. There's 670 digit, about 50,000 years. And quantum computer, if it exists, would roughly 10 to the 5 seconds. It's not even a year, right? 1/100th of a year. Right? And more dramatically, if you consider a number which is 1,314 digit, classical computer would take roughly the age of the universe. I specifically chose this number to match so that this is like age of the universe. The quantum computer would factorize in roughly 10 to the 6. 10 to the 6 is less than a year, right? A tenth of a year, okay? Maybe a month. So this is quite impressive. So what Peter shows use are key elements in quantum rules, such as superposition, unitary, and measurement. Remember that slide, that cramped slide that I have a lot of material there? They basically use that. If you understand that principle, you could actually get to the discovery of a new algorithm solving a difficult problem. How much time? I have 2 minutes? Okay, 1 minute. So in our camp, we let students discuss potential applications. So I won't go through this. There might be material we post on our websites or maybe in the booklet. There are limitations, so I already mentioned. There might be problem. We think there are problems that quantum computer cannot solve efficiently, but there might still be improvement compared to classical computer. The biggest problem is that quantum computers are noisy and have error. Even if improve the error, there will still be error. It's hard to get error-free. But however, there is quantum error correction, like encoding of logical bits, that you can actually fight against these errors. And you could solve, you can run your quantum computer even though you have error. You can still solve the problem. But you need to have a large number of qubits. And so the industry need to be able to produce high quality qubits. And you might need to connect these different quantum chips that may be the advantage of using quantum networking. So I want to end with this. So you can actually run programs. In our summer camp, we teach students IBM Quantum Composer. In our quantum programming course, we teach, for example, QuEST and Pennyland. If you know how to program, quantum computer is as real as really at your hands. And you submit their job to the cloud and to their quantum computer. So the user can actually help the industry, help the academics, help research to test and benchmark these computers and developing new methods. So it's really a playground for everyone here with different backgrounds. So I would say this is a really exciting era that we have these prototype quantum computer and you can do real things. As far as breaking the code for large number, we have not yet there. But I would advocate that education for quantum at really early stage can help stimulate interest of students into the quantum workforce. And thank you very much. This is my last slide.